Okay, finding vertical asymptotes or holes in the graph of the function, check on the calculator, and then make sure you label things correctly. We always want to make sure we label things correctly, so we will be checking on the calculator. All right, so the first example is -2 divided by x. So again, always figure out what your domain is. All right, domain is everything where x minus 3 cannot equal 0, so x cannot equal 3, and that's the important number. All right, so the domain is everything except x cannot equal 3. So 3 is going to have a break in it. Well, we want to know what type of break is it. And so the next thing is, can we reduce r of x? Well, no. R of x has a -2 up top, and x minus 3 in the bottom. All right, you cannot reduce it, which again means there's no common factors. And so that tells me that I can't get rid of, there's no way to get rid of the divide by 0. And so x equals 3 is a vertical asymptote. It should have that asymptotic behavior. As x approaches 3, r of x goes to infinity, positive or negative. And so then we'll graph it and see that that's the case. All right, so be careful when you plug it, whenever you plug in rational functions, when you divide, make sure you put parentheses around the divisor. So make sure you do parentheses x minus 3. Otherwise, again, it won't give you the right function. It'll take -2 divided by x and then subtract 3. So make sure you put parentheses around the whole denominator, x minus 3. I believe I have a standard window, and I do, and there's my graph. And so you'll see there's a break at 3, and it does have asymptotic behavior. To the left, I'm going to infinity. To the right, I'm going to negative infinity. All right, so there's my graph. Oops, that's supposed to be y, not x. 1, 2, 3, and so on this side. And so this time to the left, I was shooting up to infinity, and to the right, I was shooting off to negative infinity. All right, so it does have asymptotic behavior at 3. All right, the second example. So I've got h of t, which is t squared minus 5t plus 6 divided by t squared plus 2t minus 8. I went ahead and factored it for you, although you should be able to factor it, because I wanted you to see that this case has a common factor. Right, the top factored into t minus 2 times t minus 3, and the second one, the denominator factored into t minus 2 plus t minus 4. Now, before I do any reducing, remember we do the domain first. All right, this cannot equal 0, so t cannot equal 2, and t cannot equal -4. So the domain is negative infinity to -4, -4 to 2, 2 to infinity. All right, there's a break at 2, and there's a break at -4. But they are different types of breaks. So if you'll see this here, this is what we mean by a common factor. Right? My -2, my t minus 2, my t minus 2, that's a common factor. And so what that means is I can reduce this. That equals 1, right? When I take the same thing, right, 2 divided by 2 is 1. T minus 2 divided by t minus 2 is 1. And so we can reduce h of t. It reduces to t minus 3 over t plus 4. And then that's it. Nothing else reduces. The t's don't cancel. That's as simplified as it gets. And so that tells me I've got two different types of breaks in my function. At the t equals 2, that's the case where I get a hole in the function. When I go to graph it, there should be an open point at 2, and then to find the t value, I plug it into the reduced form of h. So I plug it in here. So I get 2 minus 3 over 2 plus 4, and so it's at -1/6. So when I go to graph it, there'll be a hole at that moment. There's an open point. Then at the other moment, there was no way to get rid of the t plus 4. So at t -4, since there was no way to get rid of that, that's my vertical asymptote. All right, my vertical asymptote is at t minus 4. I've got a hole at the point 2. So there's two breaks, but they're doing two different things. If you graph the function, you'll see that. So I'm going to go graph my original function. So I'm going to go up here before I manipulate it at all, and this is the function I'm going to graph. Make sure, again, you put parentheses around the denominator. Actually, in this case, you want parentheses around both when you go to graph it. All right, so clear. Up top, put parentheses, and we have to switch the t's to x's because I can't plug t's into the calculator, so it's x squared minus 5x plus 6 up top, and parentheses, divide by parentheses, x squared plus 2x minus 8 graph. Alright, so there is my graph. There is a break at -4. You'll look 1, 2, 3. There's a break at -4. At 2, you can't see it, but if I tried to plug 2, and 2 is here, if I go to second trace value, and I try to plug 2 in, it'll give me there's nothing there. See the y value? There's nothing there. And so you can't see it, but there is a break at 2. It doesn't exist at 2, which is why it's important to find it out, because graphically on the calculator you can't see it, but it's an important aspect of my graph. So when I go to graph this, I'm going to go over here to graph it. Alright, so first there's the asymptote at 4, 1, 2, 3, -4, there's the break. On this side it shoots up to, so on the left is when it's shooting up to infinity, and then on the right of this it's shooting down to -infinity. And then the other thing is at 2, I've got to indicate there's a hole in my function. There is a break there. It does not exist at 2, so again, and I actually know what it is at 2 and -1/6. That's the hole in my function. So we have an asymptote at 4. There's that break. And that's an obvious break, right? You look at it, you've got the asymptotic behavior. On the right, you're shooting off to -infinity. On the left, you're shooting off to positive infinity. At 2, it does not exist at 2. If you try to plug 2 in, you get division by 0. But because of the common factor, it's not asymptotic behavior. It has different behavior. It's important behavior. The behavior is there's an open point. There's an open, just a little break there, and that's it. The function continues on the same path that it was before and after the break. Alright, so again, that's the hole in the function. Alright, next example. F of x plus 2 divided by x minus 2. So again, I'm going to write it in factored 4. So x plus 2 up top. This factors into x minus 3, x plus 3. No common factors. So the domain, again, this cannot be 0, is every x such that x does not equal 3 and -3. There's no common factors. It means you can't reduce it, so there's no holes in the graph. And so that means both x equals 3 and x equals -3 give vertical asymptotes. All right, and if you went to graph it, there should be I'm not going to graph this one. I'll leave the graphing for you to do. But you can check your answers. If you graphed this, there would be a break, a graphical break at 3 and a graphical break at -3, meaning on both sides of those, as x approaches 3, my function f of x would approach an infinity, positive and negative. As x approaches -3, my function f of x would approach infinity. One side positive, one side negative. All right, but like I said, I'll leave you to graph that. We're just finding, I know my vertical asymptotes are at 3 and -3. Oops. Next example. X minus 2 divided by x minus 2 plus 3. So again, x minus 2 up top. Factor that into x minus 3 plus 1. So no common factors again, right? Domain. Those can't be 0, so every x such that x cannot be 3 and -1. No common factors, which means there are no holes in the function. Both x equals 3 and x equals -1 give me vertical asymptotes. Our vertical asymptotes. So if you graph them, and I'm going to leave you to graph them, if you graph them at -1 and +3, you would have asymptotic behavior, meaning on one side, the left or the right, it would shoot off to an infinity, and on the other side, typically, it'll shoot off to -infinity. And the last example. So again, factor, actually this one's going to take me a little work. First of all, if you'll notice, there's an x in each term, and so this is actually usually harder for students to factor. First of all, I pull an x out, so dividing it out, so it's going to leave me with x squared minus x minus 6, and then I can do the same thing in the bottom. X plus 1, right? When I take x, divide by x, I'm left with a 1, so if I multiplied back, I'd have to have that 1 to get back to it. Okay, so, and then I can factor it further. So I've got x plus 1, and then that factors into x minus 3, x plus 2, right? And factors of negative 6 that add up to negative 6. So there is one common factor, and that's the x. And that's it. That's the only common factor. And so the domain, first, before I do any reducing, x cannot be 0 and x cannot be negative 1. I do have a common factor at the 0, right? This is my common factor that reduces to 1. Right? So common factor. So it means at x equals 0, we have a hole in the function, which means an open point. And so I find my y value by taking 0 and plugging it into the reduced form. So the reduced form would be without those x values. So I take 0, plug it into the reduced r of x, which would be x minus 3 times x plus 2 all over x plus 1. Plug 0 into that. And so up top I get negative 6 over 1, so negative 6. So when we went to, if we go look at the graph, which is hard to see, there would be an open point, a break in the function, at 0, negative 6. Right? So there would be, again, I'm going to leave the graph to you. It's hard to see the break, although I think this one's a little easier to see. But at 0, at x equals 0, so there is no y-intercept, never crosses the y-axis, there's a break at the point 0, 1, 0, 6. So there's no asymptotic behavior there. The function goes up to that hole in that moment, that open point, breaks, just a little break, and then continues on in the same path after that break. Alright, then, so the other one was x minus 1, so hole at 0 at x minus 1, well, there's no way to get rid of the x plus 1. That means that has a vertical asymptote. So at x equals negative 1, there's a vertical asymptote. Alright, so this function had a hole at 0, and it should have asymptotic behavior at negative 1. So we graphed it. To the left of negative 1 and the right of negative 1, I should be shooting off to an infinity. Alright, so one side I'll be shooting off to positive infinity, typically, and one side I shoot off to negative infinity. So we graph, and I'm going to leave you to do the graph since I already did a few of them for you. But you should check that out. At negative 1, that's how the behavior of this graph should be. If you do go plug it into the calculator, make sure always put a parentheses around the numerator and denominator. So if you go check these, make sure you put parentheses around the numerator and the denominator when you go to plug them in your calculator. Alright, so that is vertical asymptotes and open points in my graph. Alright, examples of vertical asymptotes and open points. So we'll stop there and get into the next set in the next